Okay, great. So let's, okay, so we are talking rejection sampling. Okay, and then so on Wednesday, we had the uniform proposal. Okay, and the idea is, you know, you've got some target PDF, and it, you know, maybe it looks like this. Okay, I think we said f of x was 1/2 sine of x from 0 to pi for okay, and we said, well, let g of x be 1 over pi for 0 less than x less than pi. So that is g is uniform from, I'm sorry, this is g of y. I apologize, I got to change my letters here. Okay, uniform from 0 to pi. All right, and so this is 1 over pi. Now, if I were to plot this, 1 over pi is too short, and so in order to kind of get it to kind of create an envelope around the distribution, I have to multiply it by m, right? So we said m is equal to pi over 2, okay? And this becomes m times n times g, okay? All right, and kind of the process looks like this, okay? So number one, we generate values from g. Okay, well, so I'll say we generate values y from g. So y is drawn from g, okay? And then for each y value, we calculate the acceptance ratio, which is f of y divided by m times g of y. Okay. And what this will say is that, you know, in this picture, it'll say like, okay, if y gets proposed right here, then these values show up frequently, and so we're going to accept like 90% of them, 95% of them or something, okay? Whereas if y gets generated, say, over here, okay, and if you look at kind of like a vertical slice from here to here, okay, we can see that, you know, maybe only about 10%, 12% of these y values. So if y comes out and it's 3, we're going to say like, I only want to accept like 12% of these values, okay? So how do we do that? Well, for every y value that we've generated, we also generate a u, okay? So for each y that we have, okay, we generate a u coming from uniform 0, 1, okay? And if u is less than our acceptance ratio, okay, the ratio for that y, so this ratio is different for every y value, right? The y values right here have a high acceptance ratio, like 95%. The y values over here have a low acceptance ratio. So it's different for every single y value. So for each y, you have to figure out its acceptance ratio. And for each y, to decide whether or not to keep it, you generate a random u. So if the acceptance ratio is like 12%, you generate a u. And if that u is less than 12%, which will happen 12% of the time, then you'll keep it, okay? If you got a different y that's produced and you're not sure if you should keep it or not, you calculate the acceptance ratio. Maybe the acceptance ratio is 95%. You generate a random u, and u will be less than 95% 95% of the time. And so if u is less than that ratio, keep the y. Otherwise, we reject it, we throw it away. Oops. If u is less than ratio for that y, keep y as your sample, okay? Otherwise, just throw it away. So this is what we covered on Wednesday. Okay. Any questions? Or does this feel okay? Okay, and so I hesitate to do stuff directly from the homework, but we'll go ahead and do an example. I think it's a good example, okay? So here, our target PDF okay, well, I guess ideally, we want to generate values from the normal distribution. This is kind of our goal, all right? So like if I wanted to generate values from the normal distribution, but I don't have an inverse CDF, right? So, or I don't have the CDF of the normal. The CDF of the normal is like this complicated thing. I don't have it. I do have the PDF of the normal. So even though I only have the PDF and I don't have the CDF, can I still generate values from the normal distribution? Well, we can. Rejection sampling is one way, okay? And then we'll look at this transformation method in the future, which is really cool. Unfortunately, we don't use it at all, like on a practical computational level, but it's like neat that people thought of this stuff. Okay, so here's kind of our goal is to generate random values from the, we'll start off with the standard normal distribution, okay? And we have the PDF. Okay, the PDF of the normal distribution is 1 over root of the standard normal is 2 pi sigma squared, but sigma is 1. And e to the negative, and it's usually, I guess I should use z here, x minus mu squared, but because mu is 0, it just ends up being negative z squared over 2, okay? So this is what we have, right? Okay, we have this PDF, and we can't do inverse CDF because we can't figure out the CDF, okay? So inverse CDF is, a great method, but we can't do inverse CDF because we can't figure out the CDF. It's unfortunate, but we can't. So what we'll do alternative strategy. Okay, we're going to do the folded normal. Okay, and so the folded normal is just the positive half of the normal distribution. Okay. And then, and the idea is I'm going to just generate values from the folded normal. And then after I get all of these folded normal values, I'm going to just go through and basically flip a coin for each one. And if it ends up tails, I make it negative. Okay? And then then I'll get something that comes from the total normal distribution, right? So just with probability 50%, the numbers, a value generated from the folded normal is assigned to be negative, and then that will give us the regular full normal distribution, right? Okay, so alternative strategy, folded normal, and then we just, after we get x from folded normal, okay, with probability equal to 0.5, make some x values negative. Okay. The total area under the standard normal curve is 1. Okay. For the folded normal to be a PDF, its total area has to be 1 as well, right? So how can I make sure that this will end up 1? So if I integrate just f of z, dz from 0 to infinity, what would I get? 1/2, right? I would get 0.5. Okay, so then what do I have to do if I throw in a constant here, okay? What value does c have to be? 2, exactly, right? No, not a question. Okay, so we're going to just say f of x of the folded normal is going to be 2 over root 2 pi e to the negative z squared over 2. Or not zx. Okay, e to the negative x squared over 2. Okay, and this is for 0 less than x less than infinity. Okay, and so now I want to be able to generate values from this distribution, but again, we don't have inverse CDF method, so one thing we can do is we can do rejection sampling. And in this case, I cannot use a uniform proposal. What's the problem with trying to use a uniform proposal? It goes to infinity, right? So it's not going to work because a uniform proposal that goes to infinity says it's equally likely to generate the value 2 as it is to generate the value like 999 million and 10 to the a billion power or something, right? Every value between 0 and infinity are equally likely, and there's just no way to possibly do that, right? So a uniform proposal will not work. Now, you could, I guess, say like, well, I've never seen a z-score bigger than 7 or 6 or whatever, and maybe you can just generate from 0 to 6 or something, but it's going to be fairly inefficient to do something like that, okay? So uniform proposal will not work. So instead, we're going to use an exponential distribution, okay? So we will use all right, so an exponential distribution technically does go off to infinity. Right? It looks like this, okay? And it just keeps going off to infinity. And we will call this, so I'll just, we'll call this g of x, okay? Or I guess this will be our g of y. And if lambda equals 1, okay, then we have lambda e to the negative lambda x. This just becomes, or lambda y. This will become e to the negative y. actually, in order for everything to kind of, let me just switch back to x's as well. All right, so, okay, so we've got f of x is our folded normal, which we have 2 over root 2 pi e to the negative x squared over 2, and then g of x technically is e to the negative x, okay? And so what does this look like? Okay, so if this is just, so this will be the plot of g of x, and if I plot f of x on top of it, we're going to get something that looks like this. I don't know, it's supposed to look like a normal thing, okay? And both things, if we integrate them, will have an area of 1, right? And so if both things have an area of 1, and if they're not the exact same shape, there's always going to be a spot where one thing is taller than the other and another spot where the other thing is taller than the other. Does that make sense? Like, because like both of them have an area of 1, and if they're not the exact same shape, like if this part is lower over here, then somewhere else it's got to be higher over here, and meaning that there's always going to be a spot where one is taller than the other or something like that. Okay, so what I'm going to do is I want g of x to act as an envelope around f of x. So I have to scale up g of x so that m times g of x is always going to be greater than f of x in all places. Okay, so we want m times g of x to be greater than or equal to f of x for all x. Okay, so m times g of x acts as a kind of an envelope. Okay, and to kind of make this as efficient as possible, we want our m to be the smallest value so that this thing is true, okay? Okay. And so what we want is m, we're going to set m equal to be the maximum of f of x over g of x. Okay, so if this curve is f and this curve is g, all right, we want to kind of find the spot where f is much taller than g. Okay, the maximum value of f over g, and m is just gonna, like, if f here is twice as tall as g, then and that's the biggest, where if we compare f to g, then we can choose m to be 2, and then g times m will be equal to f. So this is what we got to do. Okay, so we got to do f of x divided by g of x and figure out the maximum value of this thing. Okay, we don't even care where it is, we just need to figure out what that maximum value is. Okay, so so we got to do a little bit of math here. Okay, I know life is so hard. All right, so we've got, so this is our folded normal distribution, this is our proposal, and we find the greatest value of f of x over g of x. Okay, so what is this? What is the biggest value here? Okay. I've got 2 over root 2 pi times e to the negative x squared over 2, and I'm dividing this by e to the negative x, okay? All right, so, well, this combines rather nicely. I'll get e to the, I'm going to put a negative out here, and I've got x squared over 2 minus x. Okay. All right, and so just by looking at this, okay, I've got some constant and e raised to some negative power, okay? So I can say the maximum of f of x over g of x occurs basically where this quantity, x squared over 2 minus x, is minimized, right? So x squared minus x is, is basically some kind of parabola here, okay? X squared over 2 minus x. And where this is at the smallest, e to the negative of this thing is going to be its biggest. Okay, so it's not too hard. Let's just minimize, okay? So let's minimize x squared over 2 minus x, right? And so just using calculus, we get 2x over 2 minus 1. So we get, so this leads to x equals 1. Or I'm sorry, I'm jumping ahead of myself. I have to set this equal to 0, right? Okay, and then we get x equals to 1. Okay, so this is the minimum value at min occurs at x equals 1, all right? And so the maximum value of f of x over g of x is going to be 2 over root 2 pi e to the negative 1 squared over 2 minus 1, okay? So what is this? 2 over root 2 pi e to the negative 0.5. Okay, what is this? Calculator. Huh?
Regular.
Did I regular 0.5? Oh yeah, thank you. Okay. Okay, so I punch this out and I get, okay, so 2 divided by the square root of 2, where's my pi button? 2 pi times e to the 0.5. Enter. Okay, so I get 1.3155. Okay, so that is going to be my m. All right, so okay, so the whole reason for this was that, our picture used to look like this. Okay, you've got the normal distribution here, and then you've got an exponential distribution like this. And this is our g, and this is our f. And now that I've got m times g, and if this is my normal distribution over here, m times g is going to be greater than, this is really hard to draw. Okay, this is like the worst picture, but it's going to be like this. It's going to be taller than the normal PDF everywhere, okay? That's, so, this is m times g. All right, I can't handle this. I gotta like graph it using R. wait, don't look at that. Okay. That was okay. What was I doing? All right, so f is going to be d norm. Okay, let's do a sequence. Okay, s will be a sequence from 0 to, I don't know, let's just go up to 6, okay, by 0.001, okay, and we're going to denorm of s, but we want to multiply that by 2 is our f, and then our g is d exponential of s, okay, all right. Okay, so let's go ahead and plot s versus f. Type equals L. Okay, so this is what we have here. This is our normal distribution. Oops. Let's do ylim equals 0 to 1. Okay. Okay, so we've got that, and then we'll add the lines for S and G, and we'll do a different color. Okay, all right. This is what I've been trying to draw, but it's hard. Okay, so you know the exponential is taller here but shorter here, and you know vice versa and stuff like that. Okay, so let me throw this. This is what I've been. Did I mess something up? Okay, what? Oh, good. Okay, okay. Okay, I mean, it wasn't so bad. Okay, so this is what we have. We've got, so the red is your g of x, okay, and then this is your f of x, okay? But we want g of x to be taller than f everywhere. So we did all of the work, and basically m is going to be max of f over g, right? Okay, so what is m? Okay, 1.315489. Okay, and so now we're going to multiply g times m, and we're going to plot that. Okay. So now I want f, and we're going to multiply this times g times m. Okay, and so now this is beautiful now. This is what we want. Okay. Okay, so now we've got m times g is our red line, and we still have f right there. Okay, and we can see that m times g is bigger than f of x everywhere. Okay, and we can generate values from the exponential easily, right? We did that. It was like log u or whatever. Okay, but okay, if I accept all the values, so what do I do? So we're going to generate y's from g of x, okay? So how can I do this? In R, I can just do y is random exponential, and I can ask for like 1,000,000 of these things, okay? I guess I can say rate equals 1. That's fine. And what we want to say is that, you know, the exponential is going to produce like way too many values near 0. Okay, we don't want to accept that many. For the normal distribution, we're not, like, we like 0. It's the most common value, but it's not as common as what the exponential distribution says, right? So we're going to calculate kind of the acceptance ratio here. Okay, so and you know, if the exponential generates, you know, some value like over here, then we'll accept it with probability 1, and over here we're going to accept, you know, not all of them. Okay, so we calculate the ratio. Which is going to be f of y over m times g of y. Okay, and so let me just kind of show you what f divided by g looks like. Is this? I have two things of R. Okay. So if I just do f divided by m times g, all right, and then we'll call this ratio. And if I just plot this, S versus the ratio, type equals L, okay, ylim equals, 0, 1, okay, and then let's also just do AB line, how do I do this? H equals 1, is that what I want to say? I just want to do that as well, okay. Okay, so it's, this looks weird, okay? It looks weird, but it's, this is the plot of the ratio. Maybe I'll put this, okay, right here. So if you take this divided by this, I don't know, I wish there was like some way to animate this where you're basically gonna push everything down to kind of meet this line at 1, right? So you're dividing everything by what, where the red line is. And so things above will get pushed down, and if it's below, it gets stretched up. And so, I don't know, just, if you take, you know, the black line and you divide it by the red line, you get this curve right here, okay? And so that just means values near 1, we're gonna accept every single one of them. Values near 0, we're not gonna accept, we're gonna accept maybe around 60% of them, okay? And as we get farther away, okay, like values like 3, the exponential doesn't generate values like 3 very often, first of all, to begin with, but the normal distribution generates them with even less frequency. So if we generate the number 3 in the exponential, we're going to still accept it only with around probably 20%, okay? And so, you know, if you combine that, if you say, well, the exponential doesn't even generate 3s, you know, that often to begin with, and then on top of that, you're only going to accept 20% of them anyway, then what you end up getting is something that looks like the normal distribution. So, so we'll go ahead and do this, okay? Oh, I'm doing like too much of your homework for you. Okay. I don't know. It's a good lesson. Okay, so that's what we do, okay? Well, maybe I'll just kind of write the intuition here, right? So according to the exponential distribution, we generate 0 very, very frequently, okay? And the normal distribution likes 0 a lot, okay? But it doesn't happen with the same frequency as the exponential, right? So in exponential, 0 occurs frequently. Okay. In the normal, 0 is also common, but not as common as the exponential. Okay. And so, you know, if we look at kind of just this slice right here at 0, it turns out we're going to accept, if we generate a value, if we generate 0 from the exponential distribution, we're going to accept it only around 60% of the time, okay? Yes?
In the tail of the FG and FX, as they approach to 0, will the ratio be closer to 1 since they're like very close?
They're both approaching 0, okay? But if you look at the PDF, right? The PDF of f of x is basically e to the negative, is on the order of x squared. It, something like this, and the g of x has the e to the negative x, right? So, so the rate at which it approaches 0 is much faster for f of x than it is g of x. Yeah.
So I was going to ask a similar question. What if you were to approximate something where you cannot find another distribution with a heavier tail? How would you, like, for example, I don't know, exponential? You can't approximate, like, you can't use the normal to scale the normal. You have to scale it infinitely as big as.
Yeah.
Is it ever the case where there isn't another distribution that has a heavier tail?
So yeah, it gets yeah. When you look at the tails, you kind of have to look at what you've got, and so if we're having trouble with the exponential, it's true. Like every PDF, like the tails must approach 0, right? Because the total area has to be 1. So you can't, if you're going off to infinity, it has to go to 0. And everything has to have an area of 1. So yeah, you have to try to find something that I guess has a equally heavy tail or something heavier. And yeah, if the thing you're dealing with, it already has a very heavy tail, and then you're trying to find another distribution, then it can be hard. Let me see. What is the PDF of the Cauchy? That one is known for like a super heavy tail, right? But oh, of course, I'm never connected to the internet in this room. It's like it surprises me every time. When I go, I'm just used to always being able to ask the internet for my answers. Yeah, I feel like there should always, I don't know about always. Yeah, you need something with a heavier tail. If you can't think of a distribution with a heavier tail, then rejection sampling is not going to work for you. But I feel like most of the time you should be able to something, but I don't know. Okay, so we've got this, and yeah, so the intuition is that we can take the ratios to figure out how often we should accept. And so even values like over here, 4 does not occur very frequently in the exponential distribution, and it occurs even less frequently in the normal distribution, so we just kind of take this ratio, okay? And for like values right here, okay, where like 1, like relatively speaking, occurs still frequently for the exponential, but it's like super common, not super, but more common in the normal distribution. And so anytime the exponential distribution generates a 1, you're going to accept every single one of them. Okay, and that's what this shows. Okay, so this is the plot of the ratios. Okay, and this says, if the exponential generates a 1, you accept it every time. Okay. Maybe to kind of, all right, so, you might be, you can think of this like, if you're running a company, let's say you're running a company and you need, there's like different roles, right? You need someone to answer the phones, and you need someone who is going to, I don't know, mop the floors, someone who's going to, I don't know, build stuff, someone to analyze the data, et cetera, et cetera, et cetera, right? Okay. And then just imagine you've got like a stream of applicants coming in, right? And let's say in the in the world, right? Let's say there's a ton of people who majored in, I don't know, something like where there's only a few spots, right? So like in your company, you only need like one person to draw pictures or something, right? To do artwork for advertisements or something like that. So you only need one of these, but you've got like hundreds of artists applying, right? And let's say you're, this is not the best way to run a company, but let's say you like say, I want to just kind of leave it up to chance, and so you're just going to like roll the die to see who's going to get it, right? So to kind of, what's going to happen is that if there's 100 applicants for only like one job, okay, you're only going to accept with like a ratio of 1% for that position, okay? On the other hand, if there's like, there's a great need for, this one position, and so, this is kind of what's happening with data is that like all of these companies want people to analyze their data, and there's not enough people to do a job. A lot of these places are hiring just anybody who applies, right? So they have like 5 positions to fill, and only like 3 people are applying. They're going to accept like 100% of those people who are qualified to do the job. Okay, and that's basically kind of how acceptance rejection sampling goes. Is that the proposal distribution proposes at a different rate than what the target distribution needs. Okay, and so if the proposal distribution generates like way more than what the target needs, it's going to accept only like 50% or 20% or 10% of those things. Okay, and on the other hand, if the proposal distribution doesn't generate a number frequently enough, okay, like it's below what the target needs, you're going to basically accept like close to 100% of all of these things. Okay, and so you find out where the difference between the target and what the proposal distribution, where that difference is the greatest, and that's kind of this max of f over m times g, or actually just the max of f over g, and then you accept 100% of those things. Okay, and so, as far as jobs go, there's always kind of the as the industry shifts, then there's like a lag between like the students who want to major in that thing, and then there's another lag with like hiring enough faculty members to teach all these classes. So so there's a great need in industry for data, and then there wasn't enough students, and then now there's probably enough students majoring in it, and then now there's a lag. Now we need more people to teach these classes, and so there's a lag there. And so there's always kind of this lag and catch-up effect there. That's not what we're really dealing with here, but this is rejection sampling here. Okay, we'll end there. Have a good weekend, you guys. Good luck as you study, and we'll see you all on Monday for the midterm there.